Harry Crane, the organizer of the seminar, and initiator, co-initiator. He's going to talk about probability as shape.
Okay. So the topic here, there's two very closely related parts. I want to get to entertaining the idea of what it might mean for probabilities to be shapes, but in doing so, the two parts can be described roughly as, one by the question of why is it that probabilities are commonly thought of as numbers, and related to that, what would it mean, or what if probabilities instead were shapes? Okay, so I want to think about these, and I'm thinking about these, or this concept as informally or pre-formally or pre-mathematically as possible. So when I get to the second half, when I start to talk about shapes, there will be some technical. It will get a little bit technical, but I don't want to get distracted by those technicalities. But by all means, you should ask questions to clarify at any point. But I don't want to get into minor. I don't want to get stuck on minor points, I guess is my point, is my worry. But the key questions to motivate this is I want to ask first, in what way does the numerical treatment of probability capture or reflect the underlying intuition for the concept of probability? And specifically, in what way are numbers essential to expressing probability? So when I say this, there's a few very basic questions that I need to address in order to make sense of this. And I'm going to focus mostly on this last question in particular. What does it mean for something to be probable or to have probability? So in interpreting this question, I want to make it clear that the way that I'm thinking about probability is in a very vague or ambiguous sense, in the sense that you would interpret probability if I were to ask you a question, are you coming to dinner tonight? And you would say probably. Okay. I don't want to get. I'm not giving it any more meaning than that. So at least as far as I'm concerned. So there's some concept of probability underlying that answer. You would know what you mean when you say that. I know what you mean. I can interpret your answer, or at least I can understand what you're saying. And so what is it about, particularly not just about the term probability, but what it means for something specifically to have probability or to be probable? And so in order to get me where I want to go, I need to detach myself from the conventional approaches or the conventional way of thinking about probabilities by assigning numbers to certain statements. And that's not very hard for me to do, because I think in a lot of ways, assigning numbers to certain probabilistic or uncertain statements, probabilistic judgments, I think in a lot of cases is misleading or can be easily misinterpreted. So let me just give an example of this. Okay. So this is an example that everybody's familiar with, and I don't want to go into any details about this example, because it's something that people probably have plenty of opinions and feelings about. But so I've written some more statistical discussion on what these probabilities are, what these analyses might have meant at the time that they were done. But for my purposes here, I point to this quote at the top, so this is a quote by a statistician, I guess a relatively well-known statistician, which was in the day or two after the election. That statistically speaking, Nate Silver once again got it right. So this quote to me captures, or really epitomizes this entire example, because, well, to me this statement really has no meaning, and in some way it's not based in fact. In particular, what I mean by that, I have no idea what these numbers actually mean. Okay, so for me, there might be a way to understand that this outcome was more probable than this one, but it's not clear to me in what way these numbers help to express that probability. And in particular, if you think about it, there are several proposals for how probabilities can be interpreted. So if you look at the Stanford Encyclopedia, or the online encyclopedia, there's 6 common interpretations of probability. Here I've listed 7, including the game theoretic interpretation of probability. Regardless, so none of the probabilities on the previous slide are really fit cleanly into any of these interpretations as far as I can tell. But regardless of which interpretation you might prefer, probabilities in all of these settings correspond to an assignment of numerical weights to events or to propositions that satisfy these axioms. So if we think about the set theoretically, or in terms of propositions, or in terms of sentences. And I guess my question is, what is it about these axioms that actually captures the intuition that so there is some, I guess, the intuition underlying probability theory. So depending on the interpretation is how we interpret these probabilities, and some interpretations fit better than others with these axioms. But I'm actually going to simplify this problem just a little bit, and I'm only going to think about, well, what if the third axiom was simplified just to require that the probability of an event or its negation is the sum of the 2 individual probabilities. So that gets us away. So there are some subtleties and some debate over one, countable additivity versus finite additivity, and maybe there's some other arguments over whether these axioms are satisfied maybe in some of these different interpretations. I don't want to get into that. I'm just going to assume that probabilities at least at minimum satisfy these properties, these axioms. And my initial question when I first started thinking about this was, what justifies this additivity condition? But then you might ask, well, why are probabilities assigned to be numbers at all in the first place? Okay. Now I'm not saying that probabilities shouldn't or should never be treated as numbers. I'm just debating whether they should always be thought of as numbers, and also, and I would actually suggest that in most of the cases where probability arises in everyday thought or everyday conversation, they don't actually correspond to numbers. So in that case, in what way can we understand them? So some situations in which it makes sense to think of probabilities as numbers. Well, certainly in the frequency account, frequencies are numbers. So if probabilities are defined as frequencies, then they must also be defined to be numbers. And these axioms on the previous page, these properties are satisfied, or these properties are satisfied in some way by frequencies, and so this seems to make sense. If we were to take a betting interpretation, which is done in the subjectivist account, for example, also in the game theoretic framework, then, well, if we think about betting, then we're thinking about money. Money is quantifiable, so it can be represented as a number, and so thinking about probabilities in terms of betting seems to make sense that probabilities should be numbers. But as we abstract away from these concrete settings, especially from the betting interpretation, so Bayesians like to offer this operational justification for their point of view in terms of the prices of fair bets. But the issue that I have with that is that when you then go to apply the Bayesian framework to a statistics problem or to any kind of decision problem, no money actually is transacted. So this really is just taking something that is concrete, that can be understood concretely, and understanding it abstractly, so it's unclear how the interpretation is maintained. And that's what Lindley does, more or less, in his. And he has an article in 2000 where he outlines his Bayesian philosophy of statistics. And he goes on, it's a pretty detailed, pretty long article. But he actually addresses the point of why probability, I guess why probability is a foundation for statistics, and particularly why probabilities should be treated as numbers. So he starts off by saying that statistics is the study of uncertainty, and goes on that a scientific approach to the study of uncertainty would mean the measurement of uncertainty. To follow Kelvin, it is only by associating numbers with a scientific concept that the concept can be properly understood, and that the reason for measurement is not just to make the notion of uncertainty more precise, but also to be able to combine uncertainty. So he's trying to justify, I guess, this idea of assigning numbers to outcomes in a statistical analysis, and also why the probability calculus is necessary for this. And I don't want to spend too much time talking about Lindley, but there's a few things about his justification that don't quite sit well with me, at least. And I think that this is important because of how I'm going to interpret probabilities later is, I think, relevant to statistical investigations in some way. He says that it's only by associating numbers with the scientific concept that the concept can be properly understood. But I think that this is actually backwards. If we're going to assign numbers to a concept, how can we assign numbers to a concept if we don't first understand the concept? Or at least if we don't understand the concept, that part of the concept that is relevant to assigning numbers to it. And it's also not clear to me that quantification is always helpful for understanding a concept. I think that in some ways it actually hurts, like I said in the election example, but also in cases maybe for example, in the ongoing crisis involving p-values in the scientific literature, there seems to be some ambiguity, or at least some misinterpretation or misunderstanding of what these numbers actually mean. And so while giving a number to summarize an outcome or a conclusion is a very compact way to do it, it actually brings along with it, I think, a lot more ambiguity and is more subject to misinterpretation. So ultimately is ineffective for communicating. He says that a scientific approach means the measurement of uncertainty. It's not clear to me how assigning probabilities to outcomes actually corresponds to measuring anything. Statistics is the study of uncertainty. I don't think there's anything necessarily wrong with this statement, but to foreshadow how I'm going to think about probability, he phrases this in such a way, by phrasing this in terms of uncertainty, he's in a sense phrasing probability in terms of what we don't know, what we're uncertain about, and what I'd prefer is to think about probability in terms of things that we do know, and to relate the conclusions, the things that we do know, to something that's consistent or relate a conclusion to something that's consistent with our knowledge. So I want to think about probability in terms of evidence, ultimately. Okay, and also he argues that this numerical approach is necessary or helpful in combining uncertainties, but I think that we can combine uncertainty or combine evidence intuitively. We do this all the time. I don't think it's necessarily the case that probabilities have to be numbers in order for this to be done, although maybe it's helpful in some cases. Okay. So ultimately I don't think that so where this leads me is that I don't think it's necessary to think of, I guess, when the notion of probability pops into my head, or when it's invoked, it doesn't bring along with it an essential numerical component. And here's an example that I want to maybe one more example to describe what I'm thinking. And so this was an example that Demetrius suggested. So this is something that you could walk up to somebody on the street and ask them this question. without saying anything more, and I think that they'd be able to give you an answer. In a lot of cases, I think they'd probably be able to give you a reasonable answer without having to do any kind of calculation. So I'm going to toss a coin. I'm going to toss a fair coin 10 times, and I'm going to count the number of heads and the number of tails. The question is, which is more likely, 6 heads or 6 tails, or 7 heads? And what do you expect the product of heads and tails to be? So how would you answer this question? Okay. So there's a conventional approach to this question, or a formal approach, which would say that we associate the fact that the coin is fair, we interpret that to mean that the probability of heads and tails is a half. It wasn't stated, but I'll assume that they're also independent tosses. And so under those assumptions, just using the calculus of probability, I can calculate these probabilities from the binomial distribution. So that means that 6 heads is more likely than 7, and the expectation is 22.5 for the product. Okay. So this would be accepted as the correct answer on a probability 101 exam. But I guess my question is, why is this the correct answer? In what sense is this correct? Of course, it's a correct application of the rules of probability, but why are these the accepted rules of probability? And so I would actually, I think that I would argue, in fact, that the reason why Kolmogorov's axioms have been accepted isn't that they're, in some sense, God-given, but rather that the answers that they give are reasonable. At least they're reasonable in situations. They're reasonable in situations in which we're able to develop some intuition for them. Okay. And so I guess the question is, could we provide what would an intuitive answer to this question look like? How would we give such an answer? And I think that we can give an answer to this question without appealing to the probability calculus at all. And I think I would suggest that it would go something like this. So you've said that the coin is fair. So I'm going to interpret fairness as a symmetry. So that's a symmetry between heads and tails. So you've told me that the coin will be tossed 10 times. So this symmetry makes 5 heads and 5 tails. That's the most symmetric outcome, so the most likely or the most probable outcome. And then outcomes become less likely as we move away, as we deviate from this outcome of 5 heads and 5 tails. So if we think about this, there's, say, 5 heads, 5 tails, 6 heads, 4 tails, 7 heads, 8, 2, 9, 1. So there's the most symmetric outcome is the most likely, and then as we go away from this, there is some likelihood, which we think about these as weights, although these aren't necessarily I'm not necessarily assigning numbers to these outcomes. So 10 and 0. And then again, the fairness of the coin suggests a symmetry about this midpoint. So 6 heads should have the same likelihood as 4 heads, 3 heads the same as 7, and so on. And so what we actually get is what amounts to, although this isn't the kind of shape that I'm going to talk about next, what amounts to is we get some kind of shape. We would intuitively answer that 6 heads is more likely than 7. And if you ask me what I expect the product of heads and tails to be, well, if I look at this picture, from this shape, the most likely outcomes are between 3 heads and 7 heads. So I probably expect the outcomes to be somewhere in there, somewhere between 3 heads and 7 heads, and those would correspond to products in the low 20s. Okay. So if you were asked, what do I expect, I would say something in the low 20s. Maybe I would even give a specific answer, but maybe I wouldn't. And so I don't know, I would ask this to you, whether this answer is any worse than the previous answer. Actually, I think it's better because it actually explains the rationale for the answers that I've given, whereas the previous one seems to come out of nowhere. So if you don't know probability, then these binomial coefficients are foreign. This whole setup is not very intuitive. Whereas this is an argument that you can make without appealing to any of that. Okay. So my suggestion or my conclusion is that while it's sometimes reasonable to regard probabilities as numbers, it's not necessary, and there's a lot of situations in which it's could be misleading or confusing. Okay, so that's my take on this. And so what I'm going to do now is try to think about, well, if we don't think about probabilities as numbers, but I still want to have some formal treatment of probability, how might I do it? Okay, so before I go on, so before I go on, is there any question, comments?
I'll comment. You've chosen an example that seems to be so embedded in the usual theory, opposed to all the other kinds of examples you're alluding to, where your case is so much more convincing. So I just, add the thought that when people use the word intuition, I don't know who said it, but maybe John Maynard Keynes, people use the word intuition, they think they're sort of talking about what comes naturally, but in fact they're talking about some ancient theory. And you're using words like likely, expect, fair.
Mm-hmm.
They have all been so embedded in our language in the mathematical probability theory that it seems like I gather when you said first you're going to move on to situations where this mathematical probability theory doesn't do very much for us. But in this situation where it's so, it just seems like it's not the best, most convincing setting for where I think you're going.
Okay, well, I mean, the only thing, so what I would say is, so likely, probable, I don't know what other words, expect, those words exist independently of the mathematical theory.
No, but they came into they came fair, expect, they came into, our language has been molded by, expectation was espérance, it was a translation of French espérance, it was how much you should be paid
Mm-hmm.
for it. How much do you expect? What do you expect from it?
Exactly.
Okay, here's how much I pay you for it.
Mm-hmm.
So it has this numerical.
Oh, it has a numerical, sure. But here the expectation is also a number. I guess what I'm saying, so if you're saying, what do you expect? Then I say, how much do you expect to get paid for this? You say, you give me a number. You didn't do any calculation necessarily.
I'm very sympathetic to what you're saying. I just want to say that the example seems ill-fitted because it's so embedded in our intuition in this example is probably
Okay.
We're not living independently in this theory.
Well, I disagree because I think that your intuition is tied to this example, not somebody off the street. I think that you go up to someone on the street, they could give you this answer.
They're part of our culture, the people off the street. They've been living for 300 years in a culture
that I feel I think this is a good example because it's a very difficult example because of that reason, right? I think what you're pointing out is actually the reason why this is a good example, because it would be a very difficult.
Okay. The word intuition is what is I object to.
So you don't think there's any intuition for this?
I think intuition, what we call intuition, derives from, as John Maynard Keynes said, dead philosophers. Anybody who thinks they have an intuition of something that just comes into their head, independently of the cultural history of our society, I think that's a deluded notion. That's my own.
Okay. Okay. I mean, I'm not sure how that fits, but we'll talk. Yeah.
Good point. So just, I think I have one point regarding your apprehension for numbers. I think I don't think it's always numbers which should be blamed. It's the way in which those numbers were constructed and the way in which they are represented. Right. So, for example, when I'm looking at a weather forecast and I'm looking at a figure of 60% chance of raining. So obviously I'm confused. But the reason I'm confused is not due to the fact that it's represented by a number, but because I do not know how that number came up.
Mm-hmm.
So if I dig deeper, probably they should have told me that out of all the models they tried to make a forecast of whether it's going to be raining or not, 60% of the models said yes. Now once I know, I have a better understanding of what that number means as a probability, right? Similarly, when someone tells me that your chance of getting a tenure is 20%, at the end the result is binary, right? So what does that even mean? So probably someone said that given at this point of time, out of 75 people who tried, this many got the tenure, so there's a frequency. So my point is, it's not entirely the numbers to blame, but it's the way in which they are represented is not unambiguously stated.
I agree with that, and that's what the next part will be. In other words, that I guess what I'll say is that the probability, in your case, saying 60% for the weather forecast, the probability is more than the number. It's the information that gets to that number, right? And I guess what I'm going to try to argue for is that it's in some way the evidence that you have for deriving that number. Okay, so I'm asking the question of what does it mean? So what does it mean for something to be probable? And so I guess the word intuition will appear again here. So the logic that I'm drawing off of is heavily influenced by intuitionistic logic and constructive logic or constructive mathematics. I'll use the two interchangeably here, and it's particularly very influenced by the writing of Martin Luff, who has written extensively on the topic. Okay, so before I get to what it means for something to be probable, I want to think about, well, what does it mean for something to be true? And in this case, I'm taking truth. Well, as Martin Luff writes, the meaning of a statement is very closely tied to what it means for what it means for it to be true. The meaning of he writes that the meaning of a proposition is determined by that which counts as a verification of it. So I guess in other words, if I say something to you, what it means to you is, in other words, some way of conceiving all of the possible ways that you could actually experience that concept that I've just tried to relate to you. So this ties the meaning of something directly to proof, or verification, and therefore also to truth. And so I want to take this idea, which so I'm going to call something of the form A is true or A is probable. These are judgments. I'm going to take this idea, which when I say A is true, I mean that there is a proof. I actually have proof of A, to also carry this over into probability that A is probable, meaning that there is evidence that supports A. Okay, so in any of these examples, in the example you're saying, to actually say that something has a probability means that I'm in possession of evidence that makes this thing probable. Now, what is evidence is not something that I'm going to try to explain, or try to understand. So in this way of thinking, the probability of, so I'm thinking about the probability of something to be the body of evidence for it, and then I would say that something is probable if I'm in possession of such a piece of evidence, and it's the relations between these probabilities and the evidence that makes up these probabilities that will ultimately give these probabilities their shape. Okay, but that's still a bit down the line as to what this actually formally means in terms of shapes. Okay, so really all I'm thinking about is it doesn't take it doesn't take any assignment of numbers to look at a body of to look at some argument, whether it's if it were in a court trial, to look at evidence and to assess that based on the evidence, OJ did it. OJ probably did it, right? So that's a probabilistic judgment based on an assessment of that something actually counts as evidence for the assertion. Okay. And the way that this gets formalized, so the way I'll formalize this is in terms of type theory, which I suspect is maybe foreign to most of all but one or maybe two people in the room. But the idea is that I'm thinking about statements such as "it is raining." That's a concept of rain. Concepts are things which can be known through our experience, and all concepts and judgments of those concepts are what are derived from experience. Okay, so maybe that somehow gets to Glenn's, what I would say, maybe that somehow gets to Glenn's statement. I mean, our intuition, if I say that something's intuitive, am I not just in some way calling on my experience? And whether it's an experience of a dead philosopher or not, I don't know. But it's my intuition. I don't know. But so the way I'll formalize this first is in Martin Luff's type theory. Later in homotopy type theory. Homotopy type theory is what will give the interpretation in terms of shapes. Okay. So in type theory, there's four kinds of judgments. And I write the judgment. The judgments are written in this way. So a colon is to say that A is so this is a judgment that A is a type, or that little a is a term of type A. And the way that I understand these, what I understand these to mean is that, so that I have some experience of A. So A is representing a concept, something that I've experienced, such as the concept that it's raining. A term of a type is a manifestation of the concept, or a way of verifying that concept. So walking outside in the rain is a way of verifying that it's raining. Looking through the window and seeing the rain is a different way of verifying. Then there's the idea that the judgment that two concepts are identical, such as the statement that it's raining in English and that it's raining written in Spanish. Now, this judgment would only be possible if I actually know that this corresponds to that it's raining in Spanish. But it does, or at least I know that, so I can make that judgment. And there is a concept of identity, so saying that two terms are equal. So two things, A and A prime, are equal terms of a type, or in some way of understanding identical experiences of rain, in this example. So to avoid confusion, in case you may not have seen this before, or type theory before, it's sufficient for most of this to think about, instead of terms and types, to just think about elements and sets. So each concept corresponds to a set, and the different verifications of the concept are the different elements of a set. That's sufficient for the most part. I want to think of it instead as evidence of a concept, which is related to this interpretation of proofs and of propositions. And later, when we get into the homotopy interpretation, the terms of a type will correspond to points in a topological space, and that's what'll give this shape-oriented point of view.
When you pointed it out, you said evidence of a concept.
Well, maybe I should say manifestation of a concept.
I don't know what that means.
Well, then
That line doesn't mean of, right?
This line here?
No, okay.
No, that line just is a line.
Yeah. But the things on the left are.
So I guess what I'm saying.
The relationship, that colon, what do you call that colon?
Do they call that colon anything? I mean, these are judgments. So
It's a tie.
this is a judgment, and there's nothing more to it. That's just a primitive notion.
But you translate it as tie the verb is.
Yeah, sure. A is a term of type A. Little a is a term of type A.
Evidence is a concept. That's what the bottom line is.
No. I'm saying that it's no. Little a would be evidence in favor of whatever concept big A corresponds to. So if you think of it in terms of proofs and propositions, in a constructive setting, if I have a proposition, a mathematical proposition, A can represent a mathematical proposition. Little a, the terms of this type, correspond to proofs of that proposition. So to prove the proposition, I have to produce a term of the type. To argue in favor of, maybe this is the wrong word, but to argue in favor of a proposition, I have to produce evidence for the proposition. I guess that's what I'm trying to get to in terms of this problem. When I go to a lower burden of proof, instead of proof, I have evidence.
So I'm just trying to put the things on your slide together. So, for example, truth is a concept.
Saying that
So what would be, so that is a particular concept, is truth.
Saying that something is true is a concept, I would say. I mean, I don't know what truth means.
I just read your second bullet. Truth and probability are concepts.
Okay, yeah. So I should be speaking about truth. They are concepts, but truth of what? Probability of what? Okay, that's. So the next slide maybe will help. Okay. So if I want to relate this to maybe classical logic, this is type theory. What is the interpretation of these types? So we have some basic types, some ground types, and from those we can construct new types. So think about a type as a proposition. A term of a type means that A is a proof of the proposition A. Okay. How would that be interpreted classically? It would just be to say that A is true. Okay. There's a product type, A cross B, which means that I have a proof of both A and B, proof that A and B is true, and that would correspond to this in classical logic. A and B are both true. There's important differences between these that I'll explain in a second, but I want to make sure you maybe grasp something that I was...
At one time I understood Martin Luther's type theory at one time.
Okay.
So but the words are a little bit loose here. That evidence and
Well-
concept.
Well, that's not his type theory. This is more consistent with that.
Yeah.
Okay. Now, a key difference is that so the type theory. So there's this idea of proof relevance, meaning that the actual proof that I'm in possession of might actually matter, right? Whereas in classical logic, usually the calculus is truth functional, meaning that all I need to know is that something is true. I don't need to know how it's true or why it's true or how you've proven it. And so what's the difference is that, for example, in this case, we have, so this is the coproduct. A or B means that in order to assert that A or B is true, I need to produce a proof that A or B is true. And the only way that I can produce a proof that A or B is true is to either have a proof of A or have a proof of B. So saying that A or B is true actually comes along with a statement of which of the two is true, whereas classically I can say that I can assert that A or B is true without actually saying which of the two is true. So this is kind of the non-constructive part of classical logic. I should have made clear when I say intuitionistic logic, or when I think about what's going on over here, I'm essentially just thinking about logic without the law of excluded middle. Okay. So in this case, implication, A implies B, means that I can convert a proof of A into a proof of B. Here it just means it doesn't have such a causal relationship, the material conditional, just that if A is true, then B is true. And so on and so forth. So there's various types. They correspond to one to the other in some ways, but not in others. And it's this. The difference. The key difference is that when we assert that something is true over here, it actually means that we have a proof that the statement is true. Okay. So getting back to the looser interpretation of concepts, if this is a concept, or if this corresponds to it's raining outside, okay, that's not a mathematical statement. Okay, so what would it mean for me to verify, or what would it mean for me to verify that concept? To me, that would mean that I somehow am able to experience whatever it means for it to be raining outside, which might be that I'm walking in the rain, I'm getting wet, so I know, so that's what it means for it to be raining. So I hope that, yes?
Okay, so could you clarify what, so I'm looking under the type theory column, identity type and then the proof that these two are identical.
Mm.
So the difference in the interpretation of these two, are they the same thing? 'Cause to me, the identity type, based on what you have said, seems to say that both little a and little a prime are proofs of capital A.
Yes.
So then what's the difference between that and the one below it?
Okay, yeah, so this is not, this is a little unclear, and this is the most confusing part of any of this, so I was happy to avoid talking about it, but it's actually very hard to understand if you, on a first pass. So you were right, little a, these are both proofs of A. This whole thing here, though, is itself you should interpret this as a proposition. In other words, I'm saying that I have two proofs of A. This is the proposition that the proof little a and the proof little a prime are identical as proofs of big A. And this is saying that this here P is a proof of that identity. Okay. But that doesn't so much show up I don't think it shows up very much in what's to come. Okay. This is an illustration of the constructive part of the type theory. So how do we construct a proof of A and a proof of B, an element of the product type? Well, we have to have a proof of A and a proof of B, and we put them together to make a term of this type. Having a proof of A or a proof of B, I have to be in possession of a proof of A or of a proof of B. If I have a proof of A, I construct this proof of A or B. If I have a proof of B, I construct this proof of A or B. And the point is that in constructing it in this way, I can actually recover which of the two propositions that I've proven. The implication is just a function type, so I have a function that converts proofs of one into the other. The empty type is a type with no terms, and what it means for something to be false is that if I have a proof of A is false if I can convert any proof of A into a contradiction. Just to point out here, when we're talking about, so these are dependent types, so this would be interpreted as there exists an A such that B A. But since this is constructive, in order to make this statement, I actually have to produce a term of type A along with a term of type B, a term of type BA or BX in this case. So to make an existential statement, I actually have to construct something that satisfies the condition. Okay. So this is all standard type theory. Now, I haven't said anything about probability, and the way that I want to get to probability from this is to add a probability type. Okay. So for any type, for any assertion, there is an associated notion of the probability of that assertion, or a type that would be a probability type. Okay, so the probability, so I guess perhaps confusing to some, the probability of a concept is itself a concept, meaning that the probability of a type is itself a type. This is just saying that if I have a type, then I can construct I also have an associated type, which is a probability type. And I'm going to assume just two basic rules for the probability type. One is that if something is true, then it's also probable. So if I have a proof that something is true, then I can also derive evidence. So whereas I'm interpreting terms of a type as proofs that the associated assertion is true, I'm interpreting terms of the probability type as pieces of evidence in favor of the associated assertion, with the assumption or with the idea that evidence, that proof is the highest bar of evidence. Becomes determined there from the first rule, and if I have an implication, then I have an associated implication between these two. Is this diagram commutative? I don't, well, not necessarily, but for it doesn't matter for what I'll talk about. So I'm actually not sure what the implications of that would be. Okay, so here's the basic, here are the basic elements I'm thinking about. I have a proposition and a proof of a proposition. I have a probability type, and whose terms are evidence for the proposition. And I'm going to define the probability type of the empty type. So this empty type is a contradiction. It's something that cannot be observed or cannot be experienced. So in that case, I shouldn't be able to experience or observe evidence for it either. So I'm defining the probability type of the empty type to be the empty type. Yeah.
Sorry, one more question. Can you go back to the slides?
Yeah. 2.
Yeah, right. So right here, right. So here you're talking about how you have to, if you're talking about the existence of this, you have to produce this x and y when you're talking about the existence of some a. Essentially, you get this b of a, right? So, but then I'm trying to understand how you come up with this notion of probability, right? You're not defining. It seems like probability is kind of just pulled out of the air and it's associated with this type.
Yeah.
But there's no construction for what you're referring to as this probability of the type.
So you're saying there's no description of what is in the probability type.
Right. You are claiming the existence of this probability that's associated with the type without constructing it.
Yeah. So that's a question. That's a good question. I don't know. So one way to construct. So first of all, one way to construct elements of this type is to, well, every proof gives me elements of this type. But of course, I think there should be more in there because otherwise it's just more or less the same thing, right? So that's right. So there's a technicality that I haven't quite worked out yet that I don't know how to, as we talked about this, right? It's unclear to me how to. So it's intuitively it's clear that there should be other stuff in there. It's not clear to me how to represent that formally. So that's a good question.
Is it coin toss in there?
A coin toss.
The first thing that you define which requires some probability is coin toss. So does it appear there in any manner?
Well, I mean I think that, well, that's not, I guess I don't think that approach kind of naturally translates into this, at least at first.
That's what you're trying to move away from, right?
Well, yeah, for one. But no, I mean, what's in here is specific to what this thing actually means, right? So what would be, I guess, what would count as evidence for something is something that you would judge to be evidence. So there's a way in which there's a subjective element to this, a very subjective element to this. But the question about what's actually in it formally is not an easy question to answer, at least as of now. Okay. So one more of these slides, which is important because this is what gets us into the interpretation of these types or these probabilities as being shapes, because there's a way to interpret types as shapes. And this is due. So there's a paper by Demetrius on this, which explains how homotopy type theory is typically a theory that's expressed in the language of Martin Luff's type theory, and there's a way of understanding that expression, or the homotopy types in this theory, as describing abstract shapes, and these abstract shapes are being described. These abstract shapes are formalized as homotopy types. So instead of propositions, we think about topological spaces, and I've changed the notation, I guess, to these being spaces in some universe U, but that's related to an axiom down here that is also very mysterious in many ways, but is some way crucial to this interpretation. Although I'm not sure how crucial this interpretation is to anything I've actually said. Although for me, I like it because it gives some image of what these probabilities might actually mean. But formally, is the homotopy type theory crucial? It's not clear just yet how it is, whether it is or it isn't. But so now taking these proofs, or these types over here, whose terms we interpreted as being proofs of an associated proposition, if we instead interpret the terms as points and the types as spaces, then A is a term of type A is interpreted to mean that A is a point of a space. So we have a space, a topological space, so it might have some holes in it, and A is a point in the space A. The product type is just the product space, so points, so we have a point in both the spaces A and B. The coproduct, A or B, is just a concatenation of spaces. We have a point in either A or B. The function type can be thought of in terms of observation. If I'm sitting at any point in A, I can observe a point in B. The empty type would correspond to an empty shape or a void, so a frictionless void, which has no points in it. Okay, yeah.
Is concatenation a disjoint union?
Disjoint union, yeah. So there's only disjoint union, yeah, in this. A being false in this interpretation means that we can access the void from A. So from A we can jump into a vacuum, okay, and from a point in the void we can get to any other point. So that's we don't want that. This is wrong actually. The identity type in this case is the type of all paths from A to A prime. And in this case, an element, so I don't have this here, an element of this type would be a path, a continuous path between 2 points. So this would be a point of the identity type, which we previously interpreted as a proof that two things are identical, but now it's a path.
Are these words you use supposed to be things that we would know from knowing topology? Like observe from and shape?
No, these are not. These are informal. These are pre-formal or pre-mathematical concepts. These are things that we should be able to understand intuitively. Right? I mean, I think that's right. Right? I mean.
Ideally, I would say.
So Demetrius wrote this paper. So I'm more or less summarizing it.
So in line with that, then, are you thinking of spaces as sets of points?
Well, you can think of that, but spaces can be much more than that because spaces can have more structure. Right? So a set is a space with a discrete topology, and so it's one way of thinking about it. But there might be a non-trivial topology or a different topology on it. So in other words, there might be paths. So I guess what I'm saying is, if I have a set, I have no paths between. There might be two distinct points in the space that have paths between them, but in a set, that's not the case. But you can think of them as sets, but you kind of miss out on other aspects of this interpretation.
In terms of I'm walking outside and it's raining, what is A prime and A? Can you phrase them?
Yeah, I think that's a good question. I mean, what would be two experiences of rain that are identical, but nevertheless distinct? So, I mean, if I was walking, I mean, there's a sense at which the mathematical concept, the mathematical formalism has to depart from the intuition. I mean, you could think of maybe, well, if I'm walking down the street in one direction and walking down it in the opposite direction, is that an identical experience of the rain? Well, maybe in some cases it is, in some cases it isn't. If the wind was blowing and the rain was going in my face, that's different from it being in my back. But,
If I walk in the street and I feel the rain, or I check the weather website and I see it's raining, would these be A prime and A?
So if I checked a website on a Macintosh computer and it said that it was raining, and I checked it on a Windows computer and it said that it was raining, those are two different experiences, but they are in some way the same experience. the same way to experience. Well, there would be a path in this formalization. Yeah, there was a question.
Can you give some gloss on the observatory language? Like, I don't know what it means to say something like anything can be observed from the void.
I think that you'd be better to answer that.
Well, this is a difficult example because it's supposed to express the negation, right? But in general, I would say, if you think of a plane, you're on a plane, and you have a sphere lying above you. Then from every point of the plane, you can observe a certain region of the sphere. So that's the notion of observation.
That's this observation. That's this one here.
Yeah, so I
Right.
mean, when we start talking about foundation, this is
Go ahead.
related to these questions, so I'm partly to blame for this. When you talk about foundations, right, I suppose it is a constraint, obviously, to keep things pre-formal to a very large extent. You're saying all mathematics can be encoded in terms of these notions. Yes, we already have set theoretic formalizations of these notions, but you shouldn't rely on them somehow. They should have some meaning independently. So that's one thing. So these are supposed to be intuitive. On the other hand, yes, all of these notions, what you have in set theoretic topology, can interpret this entire formalism basically in set theory, with these notions formalized the usual way. Observation will be some more or less the notion of a vibration in topology. So there are formal notions, so that gives you some guarantee that formally the system is inconsistent. But it doesn't guarantee that it's intuitive. You've kind of forbidden this word. It's difficult.
So okay, what I'll say is there is certainly there's a formal understanding of all of this homotopy type theory, and I don't want to get stuck in that. I'm kind of hung up on the informal interpretation, which you're very much to blame for, but which I didn't actually understand any of this until I read this paper, so I thought that it was very illuminating in that regard. The key idea is that, okay, what is a shape? Okay, you're taking, so the types are not shapes here, they're spaces, they're topological spaces. In what sense is a topological space, should it be thought of as a shape? Well, a topological space can be thought of as, well, it's a bunch of points and paths between points. That's enough, I guess, that may be enough to think of, to think of such a thing as a shape. So what is a shape? It's a bunch of points and the ways that the points are related to one another. Okay. The concept of equivalence in homotopy type theory would then in that case be, so what does it mean for two spaces to be, equivalent or identical, for two types to be identical? It means that there's a homotopy equivalence between the two, which you can for all intents and purposes just think of them as being isomorphic. They're not exactly the same, right? But think of them as being isomorphic, which means that there is an isomorphism that takes this structure to this one. And so in other words, two types are identical if they have the same shape in this informal interpretation. And so a witness to this identity is a deformation of one of the spaces into another. Those are homotopy equivalents. And so this is what really gives this interpretation, I think, its full force, is what's called the univalence axiom, which actually says that two types are identical. Well, the identity type of two types is equivalent to the equivalence of the associated spaces, for which you can come up with some slogans in this shape-oriented way of thinking. This is to say that the concept of identity is itself the same shape as having the same shape. I don't think that really helps, but that would be a way of interpreting this. But okay, so this is all of the machinery. Now I want to get away from the machinery in the last few slides, and I can talk about what this actually does for us.
Can I ask you a quick, simple question?
Yeah, thanks.
In your type theory, say A cross B.
Yeah.
Is that a type? Originally, you defined it as a proof of A. So A cross B, the type theory, is that a type itself?
This is a type. The terms would be.
Originally, or the proof of the type.
Yeah, that was a typo.
Okay.
Yeah, that was a type. I should say that if I had a term of this type, the terms would correspond to proofs. Yeah. Thanks. Okay. Okay. So how am I interpreting these? So just to clarify, I'm taking concepts such as it is raining. I'm representing them as shapes. The terms or the points of the shape are different verifications of the concept. So there's various different ways of verifying the concept. And to any concept, I'm associating a probability type, or the concept that it's probably raining, represented also as a different shape, whose terms are different pieces of evidence. So how these pieces of evidence actually get into the type is a question, but you can imagine what might count as evidence. If I knew that it was raining 10 minutes ago, then that's maybe evidence that it's still raining, but it doesn't prove it. Or maybe the previous day's weather forecast serves as evidence, but isn't quite enough. Okay.
Sorry, if I think about shapes then as not just sets of points, but sets of points together with specific paths
Yeah.
between those points,
Mhm.
and that's a complete picture, a better picture?
Yeah, that's better. Yeah, for sure.
Just to clarify, so I understand the concept of equivalence. So
Oh.
it's not just a bijection between points, but also you can continuously sort of morph all paths into other paths.
Yes.
Okay, so that's
Yeah.
and that's kind of the idea of the shapes that you're talking about.
Yeah, so if you take a shape, so what is, the shape of a coffee mug is the same as a donut. Right? I mean, that's, if you've ever seen this example, that would be, there's a way to continuously deform one into the other, and that's what I mean. Yeah. Okay, so what are some properties of probabilities under this? If we think of things this way, what are some properties that we can derive as a result? So as a result, we can derive first is that if A and B are identical as concepts or as assertions, then the probabilities are identical. In other words, the space or the set of things that counts as evidence for A would be equivalent to the set of things that counts as evidence for B. Of course, this is trivial in ordinary set theory. If two sets are equal, that means they have the same elements, and probabilities are defined as set functions. We get a one-way implication, which is in the case of evidence for a conjunction. If we have evidence for both A and B, then from that we can derive separately evidence for A and evidence for B, of course, because A and B implies A and also implies B. Here, if we have evidence for A or evidence for B, we can derive evidence for A or B, but the relationship does not go backwards. So this is an important departure, and so I'll discuss this a bit more in the next couple of slides. Why is this? So why not? Why can't we go backwards? Because of this idea of, well, this is related to the idea of proof relevance. So remember what I said was that if I have a proof, if in this type theory, if I have a proof, well, I might have different proofs of the same proposition, and it might matter which proof I'm in possession of. In this case, if I have evidence of A or B, I don't necessarily know, well, do I have evidence of one or the other? I don't necessarily know, so I can't necessarily go backwards here. So this is going to be a departure from the additivity axiom of ordinary the probability as number approach. Okay. There's a concept of conditional probability that I can think of here. And I think it's intuitive as to what it actually means. So notice here that so think of this as the conditional probability of B given a piece of evidence little a. So ordinarily in probability you have probability of B given A. Both B and A are just events, and you assess you compute the probability. In this case, the conditional probability actually might depend on the specific piece of evidence that you're in possession of. So this is saying, suppose that I give you a piece of evidence for A, then in what way, so what would it take for you to, given that information, to derive evidence for B that is somehow consistent with the evidence that I've given you? And what this says is that, well, in order to do that, I have to produce a piece of evidence for the conjunction A and B, and but the piece that I produce for you has to be consistent with the evidence that you've given me. In other words, I have to prove that so this is a projection operation that I didn't describe. So this is the projection of going from so A and B to A just by taking the first. This is the coordinate projection. And putting the star is, well, it's the implied function on the probability types that I can do by the rules that I've set up. So this is what it means to produce an element of this is what a conditional probability is. And so there is this equivalence that the probability of A and B is equivalent to this dependent type, which in some way resembles this resembles the so the probability of A intersect B can be written as the probability of A times the probability of B given A in ordinary probability theory. This resembles that but has a different interpretation. Okay, and the last thing I want to ask is, well, can we recover the classical probability from this setting? So in order to do that, I have to be able to in some way encode these axioms. There's some set omega that has probability 1. All sets have positive probability. And I weakened the countable additivity axiom just to this. So if this is set to be equal to 1, then I just need the two probabilities to add up to 1. But in order to do this would require that this holds for all A, and I think that this is too strong in general. What this would say is that in order to have evidence for A or its negation, I have to have evidence for one of the two. I have to either have evidence for A or evidence for its negation. But there's plenty of situations in which not only do I have evidence for A or its negation, is that I know that one of the two must be true, but I don't have any information about which of the two it is. Right? So this is typically taken to be a tautology, A or not A, but I can have evidence over here without having evidence over here. So an example might also be, well, to have evidence that a coin toss landed heads or tails, really all I need to see is the coin leave your hands, and then I can walk away and not pay any attention to what happens. But this is saying that in order to actually say that, I would have to somehow have evidence that one of the two occurred. Okay. So I think this is too strong in general to require for any A, and so maybe in some way this fits in with, this explains or clarifies for me my objection to the additivity axiom. I can impose certain constraints. So let's say if I impose, let's just say these first three, what do I get? So the first three is saying that, well, the first one is just that the probability of 0 is 0. So I'm going to now map these types to numbers. If I do that, what can I recover? So if I require that there is some type omega that every A embeds into, then that's like saying that every event that I assign probability to is a subset of omega. This is requiring, well, that every omega, every point I observe implies A or not A. That's required. That's needed to get another property, and then this is the strongest one that I need to get additivity. But if I just require the first three, then I can. So the first one, so Q2 gives me that probabilities would be between 0 and 1 if I assign probability 1 to the whole space. So I'm now thinking about these probability types as numbers. Okay, so and this would tell me that the probability of A or not A is 1. So that would give me So that would give me 2 properties. And the last one is that I would get a sort of superadditivity, that I would get the probability of A plus the probability of not A is less than the probability of A or not A. So this actually resembles, this is actually how belief functions behave. And so I guess this justifies why you must have called it the mathematical theory of evidence, but I never quite understood that. But in this case, we would get the same behavior, and I'm trying to interpret the elements of this type as pieces of evidence, and so without requiring this last one, I get the properties of, I can recover the properties of belief functions, but I have to go and make this much stronger assertion to get all of the probability, not even all of the probability axioms, just these weaker axioms that I posited here. Okay. Okay. So I think that's a good place. Well, that's where I'll stop, which is just that I've wanted to entertain, I guess I was entertaining the concept of, what is probability, and I've suggested that that probability is the shape of the evidence that favors an assertion. The justification for the axioms can be made in terms of certain symmetries or in certain intuitions about how observations fit with the way that you view the world, and what does it mean for something to be probable or to have a probability. In this setting is that, well, something is probable if I can produce a piece of evidence for it, or I can produce a point on its probability shape. Okay, but we can discuss more. Okay. Thanks.